Any question on that? This is important, a step building block, because you're going to get a little confusing as I march down the road. No questions. Now, can you sketch me the remaining pressure distribution from the surface of the water of small h to the base, where I go a depth of h? Remember the water swimming pool problem we did 3.5 months ago, but we used that to illustrate the G sub C concept, which is, if you remember that problem, is I have a swimming pool 15 foot deep, and I'm diving from the surface to 15 foot deep. How much pressure will act on my eardrum, which will hurt for that 15 feet? How do you calculate that pressure at the bottom of a 15 foot depth, or 100 foot if you're in the submarine? Anyone? Rho GH, Rho GH. And what distribution? What is the profile of the pressure look like from top to bottom? It's linear, triangle. Of which the base is Rho GH. Let me stop and make sure you understand how it comes about. Any questions? Is that clear? Okay? So far, so good. So from this diagram, the net forces due to water on the dam. Now, after we go through that argument, it's nothing but a prism, which I call the pressure prism, you know, triangular shape. Zero at the top, Rho GH at the bottom. From this, I'm going to ask myself two questions. What is the resulting force? How much in pound force or in Newton? And secondly, where? Where does it end? This has now become your static, ESM static problem. Forget about the word fluid. Once I come to this point, we are done with water. You have now just a pressure or loading distribution that is non-linear, non-uniform. Zero at one point, GH at another point. From that, based on your static, tell me what is the resultant force and tell me where is the line of action, center of pressure. Remember all that from your static? Okay? Are you ready for that? So there are two ways to do this. One is the long way to get the resultant force. There's another easier way, which is by inspection. Resultant force. A linear distribution. Rho GH at the base, zero at the top. Height is h, small. Of which the center here is h divided by 2. I call it centroid. So I want to set it up to see if any one of you can see by inspection, what is that resultant force. So for force, I need a pressure times an area. The area may be easier, I think. So let me do the area first. The area is simply the small h times the depth into the board. That's the area of which the water acts. The pressure I need to multiply that area by will be an average pressure that will be representing this linear profile from 0 to Rho GH at the bottom. Can someone tell me what that pressure is? So let me say this. an average pressure. What is that? Anyone? Yeah?
Is the area of the triangle divided by h?
Area of the triangle divided by h? No, it's not the area. It's just an average pressure, yes?
I was going to say 1/2 rho gh.
One half. Half. Because it's 0 at the top, rho gh at the bottom, and it's linear. So it's 1/2, which is the average pressure at that centroid is the pressure of which I have to multiply the area by, which is h times 1. It's not easy to see it, but let me give you a second or two to absorb this, to see if you agree. To see if you agree. Any other objection? That's the preferred approach, meaning I just by inspection come up with this resulting force. The other way, which is a little bit more involved, will be to set up a differential element like we did with differential analysis, and the coordinate of y pointing down. And for that strip of element, I'm going to formulate a differential force on that strip. The N stands for anyone? N stands for what? Net, meaning I'm not interested in the absolute pressure, but the gauge pressure, because ambient 14.7 cancel on both sides. Pressure times dA, and to get the total force, what do you have to do? You have to integrate, like we did with non-uniform velocity for continuity and momentum. So you integrate where the dA is dy times 1, the differential width of that element times the dimension in the board. Right? That's how you approach it if you don't have the insight to do it by inspection. If you follow that procedure, which I won't go into, it's just algebra, and it will be intuitive or instructional for you to do it at home, just to convince yourself you get the same answer. If you do all that, you get the same result as be done by inspection. So that's one of the two questions answered. The resultant force is average pressure. What do I mean by average? Well, turned out to be where the half rho gh depth times an area. Question on that. A step at a time, we're going to build so that I can use this to do the example problem to follow annual homework. Okay, now the location, where this resultant force will act on a triangular distributed pressure or force that vary from 0 to rho gh at the bottom, a triangular shape. Yes?
Oh, 1/3 h from the body.
Because it's a triangle, the geometric center for a triangle is 1/3 h from the bottom. This is sometimes what we call, if you remember from your statics, center of pressure, which is different from centroid. Centroid is the geometric shape of that wetted area. Center of pressure, because it's a pressure prism, triangular shape, is weighted more towards the bottom, and hence the actual center of pressure, or the so-called line of action, the location of which this resultant force will act is I should draw a new diagram. So having all this behind us, in conclusion, first, get rid of the 14.7 on both sides. This now become an equivalent free-body diagram of which the resultant force is calculated as shown, and the location is 1/3 from the bottom. 1/3 from the bottom. Any question on this? This one approach took me a little longer, but it's worth it. Okay? Now, if you have no question, my next step is I'm going to tilt the west side. I'm going to put an angle to it and ask myself, how would that change the problem? Let me do it over here. So before it was a rectangular dam, now it's a trapezoidal. And where the depth of the water is still h, the height of the dam is still cap h. And I have this angle here called theta that tells me how much the wet surface is inclined. Can you see the difference between the two geometry? Now with this caveat, can you tell me and draw the pressure prism on the right side, the wetter side of this dam? What is the pressure as the base again? What is the pressure at the base? Very good, rho GH. Nothing to do with an angle theta, because it's all dictated by the vertical height from the free surface. So it's still rho GH. What would that pressure prism look like? Let me remind you. Pressure